Okay, so do you want me to point straight to the monitor?
Yeah. Sure, don't take pictures of me, for goodness sake.
The thing is, Keith asked for a laser pointer to be used.
Yes, I've got a laser pointer here, Jim.
And what he failed to understand was the brightness of the LED display.
How long is the presentation?
So, what we decided to do is, we decided to, because we play a lot with microcontrollers and they're so really great, they're great compared to what you use in the old days with discrete components. We just thought we'd share it with a lot of people. A lot of people in my industry that avoid microcontrollers is because they're scared of them. And they're not used to them and they've never worked with them before. But once they understand how easy it is to work with them, it's actually something that they actually like doing. So we'll start the thing off. So we've got microprocessor versus MCU. So in the old days, with your computers and all that sort of stuff, like your, what is it, the Tandy, TRS-80s, they had a thing called a CPU, which is on the left, the middle red thing I can't point. And what it was that was the chip, and I can pass this around. So that's the big fat chip on there called the Z80.
We got one of those at peripheral.
And all that did, that was the main processor, but it needed input, it needed timers to be external, didn't have any built-in timers, didn't have any output control. All it had was, it didn't have serial interface, it didn't have any RAM, didn't have any ROM. That's all it was. So if you have a look at that board down the bottom there, it needed all of those. So on that board down the bottom, on that corner, we see the big chip, that's a Z80. And that's the chip that's there. And you can see all the devices that was needed to keep that thing going. Now the small little chip that's on that little thing that I'm passing around is virtually that one. That's the one on the right. So that's the microcontroller. And the difference is that everything that's on that board plus more is in that little chip. That's what's in there. So in that chip you've got an EEPROM, you've got a timer, CPU, RAM, I/O, ROM. Now that sounds a little complicated, but don't worry, we get to the easy bits. So there we have a look. So we look inside the microcontroller, which is that small little chip. What do we have? We have got built-in oscillators. We've got I2C ports, serial communication. When you're doing a lot of stuff on serial, temperature controllers and all that sort of stuff, they all come out with SPI and I2C. Then you've got UARTs, you've got timers, you've got your RAM, you've got your program memory, EEPROM, you've got your power supply reset, so it resets itself, and you've got your ports. So you've got ports that can actually input and output stuff. You've got an analog to digital converter, and you've got PWM, which means pulse width modulation, which you can use for driving motors and creating an analog output. So I'm just quickly running through, this is not stuff you have to get too involved with, but if you take a specification sheet of a chip, that's what you'll find, and it looks like a lot of, I don't want to bore you guys with that, but that's pretty much the information of a simple 8 kilobyte chip. Now you think, what the hell's 8 kilobytes? I mean, you guys are playing with what? You go to Harvey Norman, you buy 2 terabyte drives now, probably the minimum that you look for. So you can imagine 2 terabytes compared to 8K, so you think, what the hell are you going to do with 8K? But when you're actually programming down and low levels and doing simple things, that's a lot of work that can do for you, a tremendous amount. I've got an actual fact, a little sample board which I'll show you guys how to turn the LEDs on and make your own displays. That thing runs on that particular chip. And that's a solar regulator that we used to make in our company many years ago. And that chip runs everything. It used to run the display, it used to charge batteries, read currents, and everything. Just one simple little chip like that. So as you can see, it's a bit not that clear. But if we have a look over here, so you've got all the functionings happening and you've got your ports. This is where you're going to actually work and actually connect things to. And there's the pinouts of the actual chip itself. So, how do we program an MCU? Well, we need to instruct the micro what we want to do. Micros don't speak English or Italian. Sorry, Vin. I thought I'd throw that in for you, Vin. So we need a language to instruct our micros what to do. So there's a lot of things out there on how to program an MCU. There's a few different languages we can use to talk to our MCU. We've got machine code. Anybody know what machine code is?
Yeah.
So machine code is actually a low-level language. That's the lowest form of language you can get. That is actually talking to the microprocessor in ones and zeros. Ones and zeros, binary. That's how all computers actually run still today. But good luck programming in machine language. Assembly language is also a low-level language, but it's one step up because it uses text-like instructions like LDI, which means load immediate value. So I'm going to load a value into something, into a register, into memory. Structured text, that's a medium level to high level language. It's also text-like instructions. We get C, C++ and other variants. That's medium to high level language. We got Arduino sketches. I've spelled Arduino wrong, haven't I?
The difficulties.
Arduino. So Arduino sketches, but you know what? So you got basic. How many guys remember basic? There's Raspberry Pi, Fortran, Pascal. Those are all high level languages. Now, all MCUs use instruction sets with these languages, and they're all unique. So, these definitions, I'll explain to you now, these definitions to describe what you can do with the MCU. So, let's go machine language. So, unless you're a Terminator, it's impossible for any human to understand machine language, because all of these, there's an example. So, can you guys understand it? I mean, that's machine language. That's just a whole lot of ones and zeros. And basically that's what it's doing. And all that crap that you see there means Z equals X plus Y. So you can see how you're going to understand that. It's virtually impossible. Impossible. No one actually programs in that. But you can imagine the forefathers of microcontrollers that probably sat there with a whole lot of dip switches and actually did their first programs. Yes?
I actually still have in my cupboard the 1976 mini-scamp project from Electronics Australia, which has switches for your input and red LEDs as your output.
And it works, but if you've got a problem in your program, by the time you've got to line 10, you don't know which one is in the right spot and which zero is in the right, so it's become extremely complicated. Assembly language. Even though it's a low-level language, it's more human-friendly and not that hard to get your head around. I work a lot with assembly language. It is a low-level language, and the compilers are directly convert to machine code. So you write something in text, and it converts it directly. Very simplistic. There isn't a lot of stuff. This allows smaller devices to be used in projects. So, for example, there's an assembly language, so MOV means move. So I want to move EBX into ECX. Now you notice that I've gone from this side to that side, because in programming you move from the right to the left, not the left to the right. And that goes for the data as well. I'll show you later on. So there we go. So you're talking English, so I'm going to move EBX into ECX. The next line is I'm going to move EDX. Now what the hell is EDX? That could be registers, that could be values, and I'm just moving them around. And the reason I'm doing this presentation like this is so that you get the basic understanding. You don't have to learn, but you can get the basics. So for example, if I want to place a value of a stored register to an output, so a register, all it is think of a bank of switches as a register. So I've got 8 switches. And I set those switches, bang, 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 say 3 of them on, 3 of them off, and the last 2 on. Now I want to output that. I would use the command in assembly out to port A, register 16. So whatever I've got in register 16, I'll output to my port. That's previously I just showed you the microcontroller's ports. So there's my CPU, I've got some RAM, and there's my ports. So then I get whatever's in register 16 and I output it to port A. Easy. That's pretty much how assembly language works, by just using that command. Let's have a quick look at C language. We won't delve too much in it. This is pretty much an example of C language. You can see that it's got its main structures in the beginning, so it includes something like a file. So an AVR means that's the processor we're using. You'll always see that C programs start with the void thing on the top there, and then the brackets open, and you go ahead and you assign things. I won't go too much in depth with this. Simon might do a little bit of it later on. I want to try and come through as much as I can. But the remarks on the side, as you can see, it's very text-based, and you can see what it's actually doing on that side, and it's telling you, yeah, is the remarks of what it's actually doing on that side. So that's pretty much C language. Then there's all the others. We have structured text. Some of you might recognize some of this stuff. There's Pascal. You don't have to understand this. I'm just showing you how they're different, but they all sort of seem to have the same basic structure. Python, there's Python. If you guys like to play, there's Fortran and Basic. Do you guys remember Basic? Good old Basic. Does anybody remember that? Yeah, see? As you go down the line, you do the instructions. Yeah, go to 160. If vertical, go to 100. Then start drawing a circle. So that's a little program to draw coloured circles in Basic.
Basic was an interpreted language, wasn't it?
Yes.
It wasn't assembled.
No,
it was interpreted.
it's quite a high-level language.
It was,
Basic.
yeah. I remember using IBM's macro assembler, and then I went and used Eric Isaacson's A86 for assembly language. It was much better because he designed the 8080 chip.
Yes.
So he optimised his assembler for the 8080.
So when you want to start playing with microcontrollers, it's good to just know a little bit of things, but the most important thing you must know is those two things. It's the most important thing that you need to know when you want to start playing with microcontrollers and digital stuff, any digital stuff, even gates. Right? This is it. So this is the part that's important. So we have, that is what we call a byte. So that's 8 bits. 8 bits equals 1 byte. And if you have a look at it, it starts, like I said to you, on the right and moves to the left. Unlike when you're reading something, it's the opposite. The point of the bit is actually the key. So even though we've got ones and zeros, if you have a look in those blocks, that's your bits. So that's off, that's on, off, on. Basically that's it. That's got a value. And it depends where that bit is in a position on this thing. So if I took this bit and it was all zeros and I put 1 here, it's still only 1. But if I move it to here, it's still 1, but it has a different value now. And if I move it there, it's got a different value. So that word actually, that byte, not a word, because a word is 16 bits. So there we have 1 byte. And that equals 150. So 0, 1, 1, 0, 1, 0, 0, 1 equals 150. How does that happen? Well, easy. You just add up what's there. So we've got 2 plus 4 plus 16 plus 128 equals 150. You don't add that because it's 0. You don't add that, you don't add that, and you don't add that. So if we added 2 plus 4 plus 2, we're going to calculate if you want. 16 plus 128 gives you 150. So that value of 150, that's what a binary word looks like. As simple as that. And that first bit there is called bit 0. So in actual fact, although there's 8 bits there, this is called bit 0, and that's called bit 7. And you can actually see, there's the 7. So even though it's got a position, it's still called 0. Wouldn't be easier with a pointer, I think that would be So there we go, we've got 1 byte, 1 bit. Have I lost everybody yet?
Yeah.
Have I?
You go.
You going okay?
Yeah.
If you guys need me to explain, I will. Hopefully after this you'll be programming your own microcontrollers. You won't be so scared of it, there's nothing wrong with it. So there's the value chain again. So look at it, I've got something there for you there. If we took a binary value of 101001, so they're all alternating, the value of that, because if you have a look at the scale, so it starts 1, 2, 4, 8, 16, 32, 64, the position of those bits equals the value. So if we add it down the bottom, what we got there is 1 plus 4 plus 16 plus 64, and that equals 85. So that little word byte there is actually equal that. Reads left to right. And that's what we always do. Sorry. Right to left. Give me some more, boys. All right, now that's called a byte. A 16-bit is a one word. So a word is 16 bits long, and a byte is 8 bits long. And you can see nothing changes; it just gets bigger and bigger. So your computers at home, 64-bit, all that's happening is this is growing bigger and bigger and bigger and bigger. So if you had just 1 here, it could be 1 billion. And that's what I'm saying. So at the moment, as you look at the value, it goes up. So we're finishing off with our 8 bits there. Now we carry on with our next 8 bits along there. So we've got, even though it says 15, there's actually 16 places. And we go up to 32,000. But if you added them all up, we get down to the bottom figure, which is 65,000. So if we had 16 bits and they were all on, that value would be 65,535. Does anybody understand the positioning of that? Wow, okay.
Hang on, what did you have there at one? Yeah, one song, sorry. What was that, 65,000?
65,535.
How did you get that?
If it was all, that's the maximum value you would have if they were all on.
Yeah. 15 bit.
Yeah.
16 bit.
Right, so working with ones and zeros, which we've just done there, is a big task. It'll drive you crazy. So what they did when they were working out programming, they invented something called hexadecimal, right? Because we need to convert binary into something more palatable and easy to understand. So there's hexadecimal. So that makes it one step easier for the human to understand. So binary, now this is the interesting part, I might just quickly do that. We get nibbles. So you've got a byte and now you've got a nibble. So a byte is 2 nibbles. So you've got a low nibble and a high nibble. So the byte is 8 bits, you've got a low nibble and a high nibble. So if you have a look, they've done this on purpose so that it makes you easier to understand. There's also things called octal and stuff like that, but it didn't work out that well, so it's not very common to use octal. So hexadecimal is a real thing. So this is actually now getting to the part where actually, if you actually looked at some programming and manuals in computers, you'll actually start seeing some letters happening there. So what they did is, if you look at the binary, they broke up the byte into 2 sections called a high and a low, and you've got your binary there which goes up to 4 bits. So that's 1 nibble. And that's how the hexadecimal actually works. So what actually happens is, for example, if I have 1011 plus 0111, it actually, that one on that side equals 11, and this one on this side equals 7. Now if you go down to your table and you have a look and see what the value of decimal is, so we've got 16 values because, like we said, remember, that's 1, that's 2, 3, 4, 5, 6, 7, and you can see now you're in 8. And if we go back to what I was showing you earlier, just quickly, see, if I do that, you can see the values. I don't know if you saw that. Alright, I better just speed this up quickly. And we can convert hexadecimal back to binary. So CA would be 12 and 10, and it would be 1100 or 1010 on the bottom. That's hexadecimal. Anybody lost? Everybody's lost. Alright. Okay. Then of course we've got ASCII code. Now, you won't be able to understand ASCII code if you didn't understand what I was just telling you now. So there we go, there's ASCII code. So everything in the whole alphabet is there. And that stands for the American Standard Code for Information Exchange. So if I wanted to print something to a printer, and I wanted to print M, or for example, oh, we'll do something, let's do something. So we say, right, A is 41 hexadecimal or binary. Now, which is easier for you to understand? If you looked at that, you looked at the binary, 0100001B actually doesn't really it makes more sense to see 41 hex, and you can go and have a look at the hex in the table, and if you have a look, it's capital A. So it's a third column, second from the top. Hexadecimal. Right, example. We want to send IARS to our printer. We will send 73 hexadecimal, which is I, 41 hexadecimal, which is A, R, which is 82 hex, and S, which is 83 hex. That's it. So that's the binary codes for them, and that's the hexadecimal codes. Instruction sets. Right, according to Google, a complete set of instruction in machine code can be recognized and executed by a central processing unit. That's a little chip. So what is a basic instruction cycle? This is a basic instruction cycle of a microprocessor. We start, we fetch an instruction, which is a fetch cycle. So we go and fetch that out of your ROM. We decode it. What is that instruction telling us to do? Put the kettle on, go and have a pee, have a beer. Right, okay, execute that instruction. Don't have that beer now, because you know what to do. You've decoded it. It said to you, it's a code book. It said, go and have a beer. You have a beer and you go back and you have another one. If it's the same instruction. And eventually you'll have to stop.
What's me?
Now where that happens in real life is you have a program. There's a program that runs your hot water system. Let's say we're having a program that runs a hot water system. So the program starts, it reads a temperature sensor. Temperature sensor says, I'm too hot. What do? Yes, I'm too hot. Turn off the heater. Wait for 60 seconds, go and read the temperature sensor. That's a program. Read the temperature sensor. Are you still too hot? No. Turn on the heater. Go and wait for 60 seconds. You're 60 seconds up, go and read the temperature sensor. That is pretty much a flow chart of a program that you want to write for your microcontroller. Does that make sense?
Yeah. Absolutely.
And you just keep doing it. And that's what micros do. They just relentlessly keep doing the same old thing over and over again. I just thought I'd throw this into this. So in instruction sets, there's assembly again. So there's an example. So you're not going to be lost, because when you download, if you want to work on a microcontroller, whether it's an Atmel or a microchip or a national semiconductor or whatever, any one of those Panasonics or whatever, they all have an assembly, and there's the instruction set there. So it's very simple. See, add means add. I'm going to add register R to register D. And so it's very, very simple and straightforward. Some registers, and there's an instruction set summary blown up. So there what I was showing you earlier on, and we can do some logical gates. So if you've got your gates that you used to use in your discrete components, AND gates, NOR gates, it's all in there now. And instead of having a separate OR gate or NAND gate to do that for you, and an AND gate means I've got A and B before I have C. An OR gate is I can have A or B and I'll give you C. So basically it's done now in the software. It's not done with chips anymore. And that's the beauty and the power of microcontrollers. Example. using binary, hex and instructions, I want to output the value of a 7-segment display to show 2. Right, so I've got all my LEDs there, I've got my chip. Now I want to show 2 on my display. How do I do that? We need to turn on the following LEDs. So what LEDs do I need to turn on to make 2?
A, B, G, E, D.
Beautiful. And I leave the decimal point off because I'm not asking for one. And I'll leave F off, and I'll leave F off. And I'll leave C off as well. So there we go. So we need to turn on A, B, D, E, F, and G. Now if I'm feeding that with a binary signal, this is where binary comes in. I need to switch on those segments. There it is. There's my binary. I'm switching on A, switching on B, not switching on C, switching on D, switching on E, not F, and G. So that value is a binary that's going to my display. And it is 5D hex. And if we've got time, which we might not have, we can actually put 5D into that microchip and we'll turn the little display on and show 2. It's easy. So that's the values of the binary position. There's your hexadecimal chart. So if you have a look, we've got 1 plus 2 is 3, plus that is how much? 11. Am I right? So 11, what is 11 here? I can't really see.
1011 will be.
So B. And over here I've got 1 plus 4 is 5, and 5 is 5. So what I'm sending out the microprocessor is 5B, 5BX. And what I want to do is when I write a program, easy. I'm going to load in my register the value of 5B into register 16. And after I've written that command in assembly, I'm going to pick another command called out. And I'm going to output register 16 to port B. Done. That's it. Done. So all I do is I load in 5B, that's the command you write, into register 16, and I output that value to port B, and I will turn on number 2 on that thing. For example, there's a C, so that's assembly, and that's the C version of that program. And you can see it looks a lot easier because it just says port B is equal to AA, but that's, I didn't actually modify it for that. So AA is something else. It's actually not 5B, but I'm just saying that's an example of C. Right, so when you've got a microcontroller, try and push this, you need to set up your ports. So a microcontroller's got ports on it. There's pins coming out of it that can be set up for analogues, inputs and outputs, and all sorts of stuff. So all micros have multifunction ports. You've got input, you've got outputs. There they are there. Oh, what have you got? You've got UARTs, you've got counters, you've got timers, you've got analog to digital converters, everything. So you've got digital. What have we got in digital input? A Morse code key. So you want to read a Morse code key or keypad. Or you can read an analog signal. Like a pot, trim pot, or temperature gauge. Some temperature input into something like that. Digital outputs. You can have a relay, you can have a display like I showed you early on, or you can have some analog signals coming out of it as well, an S meter for your radio. So there's an S meter there, and basically that's it. And you also can have some sound coming out of it as well. And then on top of that, the micro can also do communication. So it can actually communicate with UARTs to get your digitals and inputs and outputs to be sent over serial communication or radio.
Can I just interrupt for a second? Just back on that one there. It's a bit off topic, but the word digital there, I recognise that as a trademark of a company called Digital.
Okay.
Is it?
Yeah, it's good.
Yeah,
They're gone. I was about to say, whatever happened to Digital?
I'll probably, you know what, if the guys that manage copyright of Google...
I'm not worried about your
probably
copyright.
come and arrest me for all the...
No. I'm not worried about copyright. I was actually curious about digital. Because when in the mid-80s, when I worked in the Electricity Commission, you had The mainframe computers of the day, as they called them,
digital.
were digital VAXs.
Yeah. Well, that's probably where I pinched it from.
Oh, okay, yeah. But okay, but the company
So now we want to set up, we've got our chips, we want to set up our ports. There's our chip there, we've got a port B. So let's say we're going to work on port B. So for goodness sakes, I don't know the people that actually designed these chips in the factory, God knows why they put 2 port Bs up there, 1 down the bottom, and 4 coming up. Fuck knows why they did that. Why they didn't just stick into one side, only God will know why. But anyway, there we go. We've decided we're going to use port B. How do we set it up? So in the book it tells us, there we go. We have 3 things on that port. We have the actual port itself, the value, we have a data direction register, and we have the input pins. So if you have a look, what that actually does, that's the port value output. So you can read what has been set. This tells you whether you, on that chip, whether you want that port to be an input or an output. So if I put 1 there, that port's going to be an output. If I put 0 there, so we're back to our binary again. See, if I wanted to put binary there, I can actually do that now because I understand what I'm doing. And that's the port input value. That's actually if you want to read the input. So if you've got a button or a switch, so those are registers inside the microcontroller, and that's their names. Their names are port B, DDRB, and pin B, or whatever the case is. So that pin B means port input B. DRB means the data direction. So what you've set that to when you start your program. So if I want to set up my ports to first 4 inputs and the next outputs, I'll set up DDRB to 0001111. So that means my first inputs on that would be, so my pins number 4, 5, 6 and 7 would be all inputs, and 1, 0, 1, 2, 3 will be all outputs. And then what I will do is I'd load that into the register and I'd add it. So I just output. You see what I'm doing? Just simple stuff. Then I'm going to clear the port and set up pull-up resistors. Now this, when you're playing with electronics and microcontrollers, that's a very interesting thing that's going to come up all the time. Pull-up resistors. It doesn't matter what language you're writing in, you're going to come across that. So inside a microcontroller, you don't have to, on the external, you don't have to put resistors to hold ports down. You can actually set them inside. So inside the microcontroller there's a resistor, and you can turn that resistor on, or you can turn it off, and it's on the pin. So if you want to turn them on to keep it, so for example, why would you use it? Well, there we go. There's 2 examples. I've got that little tab there is the actual pin on the microcontroller, and I've got pull up and pull down. So if I want to pull it up, I'm pulling it up to 5 volts, and if I ground that pin, that's it. That actually will pull that pin down to ground, and that's a state change. The other one is I pull the pin down with the resistor, and if I put a positive pulse on it, then it also operates the pin, and that's how it actually works. You understand the difference between pull up? That's actually quite important, not just for microcontrollers, but if you're looking at pull up and pull down. So pull up, the one that's there, is actually called an NPN. And you'll see it in when you're working on a repeater. It'll tell you what the input of it is. Is it a PNP input or an input? So, and the pull down is actually a PNP because it's actually putting power into the unit. Okay, and then we've got read port pins, there we go. So analogues, resolution. I don't want to go into too much depth here, but there again. For example, we use 1, 2, 3, 4, 5, 8 bits. 8 bits to control the things. 8 bits, maximum 255, 256 combinations. So I could have 256 combinations with 8 bits. I don't want to lose you guys too much, I just thought I'd put it there. So there's resolution. With analog, I'll probably just move it on quickly. So, for example, analog converters inside your microprocessor need a reference. So something's got to be referenced to it. For example, you can have a 2.5 or 5 volt reference. If we have a 5 volt reference and an 8-bit digital to analog converter, we would need 5 volts on the analog input pin to get a full 255 points. So if I wanted to fill up that word, or that byte, sorry, with full with ones, which gives me 255, because if I actually added them all up, I've went 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 will equal 255 points. If I wanted to fill it up, I would need to then put, if I had a reference of 5 volts and I put 5 volts on my analog input pin, I would get 255 points. Okay? This is the interesting part. So this would mean that for 5 volts divided by 255 points, I did the maths for you, equals 0.196 volts per bit. So if I put 0.196, so if I put 19.6 millivolts on my analog input pin, I will show 1 bit in my register. It will show 1.
Okay. Just tell them what the reference makes quickly, so they understand.
What?
Like the reference,
So the reference is a pin on the microcontroller that sets up the internal reference of the analog. So that's the maximum voltage. So if you set up your reference to 2.5 volts, that means if you put 2.5 volts on an analog pin, it will fill up the register, whatever it is. So for example, if we have a 10-bit analog to digital, we would have 5 volts divided by 1023, because 10 bits gives us 1023. 8 bits gives us 255, but if you add another bit and you add another bit, it adds up to those. And for 2, you get a bit, you'll obviously at 2.5 volts, you'll get 0. So it equals to 0.0048 volts per bit. This is where it becomes interesting. So right, now you can see why it's a good idea to understand binary and hex. So if I'm setting up this is a register inside the microcontroller, I'm going to now set it up. I can now inside, I can set it up to 2.5 internal, because it's got an internal reference. So I can actually select that, it's not a problem. I wouldn't worry too much about that bit, because that just adjusts the analog, whether you're going to read from left to right or from right to left. So we just leave that as a standard, which is from left to right. From right to left, sorry. Alright, so let's have a look. So, we have our tables in our book. Okay, so we're looking at 2.5 volt, looking at that particular analog ref there. So inside, that's my register inside the microcontroller, and I'm going to be using it for analogs. I'm going to go and set that to 1.1. Because why? I want to pick up 2.5 volts. So I have a look, res 1, res 0, I'm picking them both 1.1, and if you look at the bottom of the table, what does that say? Can't read it. You can't?
I read.
Resolution
Yeah,
is 2 quarts.
2.5 volts.
2.5.
You need a 40 bit
It actually says 2.56. Right?
With external capacitor.
Now, what we're going to do is we can leave ADR as 0, because we're not going to change it. Alright, so we have a look. So now we're going to use analog input 3 of the chip. So we're using analog 3, we go 0, 0, 1, 1. There we go. And that is this one here. 0, 0, 1, 1. I'm using the input 3 now. I'm using the input 3 of the chip. Right? So now what we have is that in hex, we have that in binary. And what we do is to set up the analog, we load that into our register and we output it. Done. So that's our analog setup. So we're actually now going to set up the analog port hardware. Okay? I'm done 15 minutes and I'm done. We set up the ref. We set up the ref to 2.5 volts. Remember that before? There we go. There's our 2.5 volts equals 1024. There it is there. I'm not going to go too much into that. Now if we wanted to measure 12 volts with 1 decimal place, we need a value of 120. Okay? We have 102.3, so we've got more than enough bits, so we could read 102.3 volts if we wanted to, with a resolution of 100 millivolts. Therefore 12 volts is way too high for 2.5 volts. So if we put 2.5 volts on the input of our pin, it's going to read 102 volts straight away. So you remember that 2.5 ref, we need that 0.0025 volts per year, 24 millivolts, or 2.4 millivolts, sorry. This means we need to get 120 times, sorry I did the maths for you, 0024 volts per bit. So we need to get, to be able to read 120 in our register, we need to get 0.928 volts on the input pin. So we need a resistor divider. Here's our resistor divider. We have 12 volts in, 0.29, there's a bit of a capacitor there for some decoupling. So there we go, I've just grabbed some values, can be anything, but that pretty much gives us, there's IVR, Ohm's law, and there we have 0.2983. So there's a little bit of a difference, just using common values, so you could probably use a variable resistor or something to do that. I'll better speed it up, Simon. Voltage shifting, so when you're working with microcontrollers, what's the biggest problem? They run on 3.3 or 5 volts. Amateur radio runs on 12 volts. So if you stuck 12 volts in the input pin of a microcontroller, you're going to let the smoke out. So once we've set up our ports as previously noted, inputs and outputs and pull-up resistors, we can connect our MCU to the outside world. What does NPN mean? This is what we're going to do. So for this one, if I put a Zener diode of 3.3 or 5 volts, I can feed 12 volts into that pin. And what will happen is, it'll limit that Zener diode will limit the voltage to 5 volts. So I can put 24 volts on the input here. If I put 24 volts in here, doesn't matter what I put here, that will clamp it, and then the micro will only see 3.3 or 5 volts, depending on the Zener diode. And that will be called PNP input. Or we can use an optocoupler, or we can, for NPN, we can have the MCU with a pull-up resistor, and we have a diode. When you short that down, that's pretty much how repeaters work as well. When you short down, the PTT works. So it doesn't matter what you do there, you can even put 12 or 24 volts and can't go back through the diode and can't damage the microcontroller. And we've got the same thing for outputs. Outputs as well. PNP output, you drive it with the transistors, and there's some information, I'm sure you guys will know what that's all about. I'm just running through this a little bit because you guys know what that is. I don't have to explain too much, I'm sure. And we want to get on to Simon thing. Getting more for less is the last slide. So what do we want to do? If an MCU chip only has 16 ports, we can do things called multiplexing. So we can actually get 32 outputs for 12 pins. And that's by doing multiplexing, so they all share the same bus. Same thing with that picture over there. We can get 16 heads to run with only 6 pins. Multiplexing. Our keypad, we can get 12 buttons for 7 pins. So the micro only needs to have 7 pins, but you can read 12 buttons by multiplexing. So you can do scanning and all that sort of stuff. Alright, adding peripheral devices. We've got latches and all sorts of weird and wonderful devices. You guys might know this, the guys that played with old computers and all that, the 8255. Very common chip to go with the Z80s and the Intel 8080s and 8081s. Is this 8255. It's actually an Intel chip, and what it does is it expands the bus. So you put your data into it and you can actually grow, and that's by multiplexing. That's all. I had to rush to the last year because I was running out. Any questions?
Good.
Any questions?
So you get that kind of movie.
What happened to John Corporation?
It's a lot to push through, but I just wanted to show you guys it's not that bad. It's not that hard. If you want to do a project with my project, it's not that hard. It's not just going to